Okay, so I will talk about the role of inheritance throughout the Wilson cycle and illustrate my presentation with the example of the North Atlantic rift system in Western Europe. So the Wilson cycle is a theory that states that orogens and the rift system form one following the other following the same lines, which implies a very important role of inheritance. And the North Atlantic rift system is a very particularly well-suited place to study the impact of inheritance because the North Atlantic is a single rift that affects two different orogenic belts, namely the Caledonide belts to the north, here in green, and the Variscan belt to the south, here in red. And when we look just on a large scale, we can see that in the North Atlantic, the North Atlantic rift system followed the Caledonide suture zones, but in the south, it cuts, either it surrounds or it cuts with high angle the Variscan orogen, so it doesn't follow the suture zone, which means that inheritance is not, orogenic inheritance is not necessarily reactivated in the same way. And the question is why? A first difference between the Caledonides and the Varicides is their formation. Indeed, the Caledonide belts resulted from the closure of one major ocean, which is the Iapetus Ocean, following a protracted subduction of more than 3,000 kilometers ocean. In contrast, the Variscan belt resulted from the closure of several narrow oceans that were presumably less than 500 to 1,000 kilometers. So the question, when we look at the characteristics of rifting in Western Europe and compare what happens in the Caledonide domain compared to the Variscan domain, we can also see other difference. A first difference is that in addition that the rift follows the suture zone in the Caledonides, the orogenic collapse of the Caledonide orogeny was magma poor, but its rifting was protracted, polyphase, and had a magma-rich breakup with lots of magmatic addition, which are represented here in hatched pattern. And the duration of the rifting was very long, from more than 80 to more than 100 million years. In contrast to the south in the Variscan realm, the orogenic collapse was magma-rich, which is represented by this pattern here. The rifting was much shorter, from 20 to 45 million years about, and the breakup was magma poor. Here we have exhumed mantle. So the question is, in the framework of a Wilson cycle, what happens if a basin doesn't go throughout the entire drifting process, but if a small basin closes? Are there differences in the orogeny? And to answer this question, the first question is there a difference in the architecture and lithology of hyperextended rift system compared to mature oceans? And are there different in subduction-induced processes when a hyperextended rift system is closed compared to a mature ocean is closed? So first, we compared on a very first order the nature of seafloor between basins that are narrow and wide. And we realized that narrow oceans that are less than 300 kilometers wide usually do not show a mature oceanic crust. We call them immature. In contrast, oceans that are wider than about 300 kilometers usually display steady state Penrose type oceanic crust, and we call them mature. The next step was to compare the architecture of rifted margins. So to do that, we measured the width of different domains. Here is the necking domain, the hyperextended domain where the crust is less than 10 kilometers to the euro, and the exhumation domain where we have exhumed mantle. And we got average values of each domain for rifted margins. And then we compared the width of each domain between mature oceans here in black and immature oceans here in yellow. And what we noticed is that there is no difference statistically between the width of the domains between narrow, immature and wide mature oceans. Then the question was about their lithology composition. So for each domain here, we regarded the composition, the lithology of the domains. So to think about that, we looked at how lithology evolves during rifting. At first, when we form the proximal and the necking domain, there is little modification of the lithology of rifted margins. The ductile layers here represented with this pattern are just progressively thinned out. But then when we go to hyperextension, we have important circulation of fluids here in the hyperextended domain. And we have fertilization of the mantle by impregnation of melts from the melting asthenosphere. So we have beneath the dome of exhumed mantle a fertile lithospheric mantle. Then when we go to seafloor, steady state seafloor spreading, the mantle is depleted and we have this residual Harzburgitic mantle beneath a steady state oceanic crust. So that's the state of a mature ocean. And an immature ocean stops before the formation of oceanic crust, so he doesn't show this depleted mantle zone. So the main difference between mature ocean and immature ocean is the existence of this depleted mantle and overlying oceanic crust. Now, what happens when it comes to subduction and collision? Well, on the first order, whatever we close a wide ocean or a narrow ocean, you have a similar first order architecture of orogen. You have two buttresses, which are usually formed by the necking zones of each margins. A part of the material that is accreted, scrapped off the oceanic crust, and that happens here to be here in the internal part or the orogen, and a part of the material that is subducted here. So on the first order, the architecture is the same, but when we compare the scale of the processes, we are not looking at similar processes at all. And to illustrate this, I display here a tomographic view of the Pacific plate subduction. And I compare it with a subduction of the Pyrenees plate beneath France. And this square here has the same size as this square. So when you compare this to this, you can easily imagine that the processes are not the same. And indeed, what is the difference between a mature subduction? During mature subduction, the oceanic crust goes down deep into the mantle, into the asthenosphere, and melts. This results in the formation of a magmatic arc on the upper plate and a depleted mantle beneath. In contrast, when you have a narrow ocean, the lithosphere doesn't go deep enough to produce magmatic, magmatism, and there is no magmatic arc. this is well illustrated, for example, in the Alps, where there is no trace of a mature magmatic arc, and in the Pyrenees, where it's the same. So an orogen that results from the closure of a narrow ocean is usually less, it doesn't display a magmatic arc, and the lithosphere, the mantle lithosphere beneath is much more fertile compared to the mantle beneath a mature upper plate of a mature subduction. And this may have implication for the subsequent tectonic events, because when you have a depleted mantle, you may not have enough material to melt to form magma. So during a collapse, following a mature subduction, the collapse of the orogenic range will be magma poor, in contrast to the collapse of orogen resulting from the closure of a narrow ocean.
Pauline, you have 4 more minutes.
Okay, I'm coming to the end. And this fits well with what we observe in the North Atlantic rift system, because here in the Caledonian orogen, which was the result of a mature subduction, we have a magma poor orogenic collapse, in contrast to here in the Variscan realm, which was the result of the closure of several narrow oceans. We have a magma-rich collapse. And this collapse influenced also the subsequent rifting event, because here the mantle was terribly depleted by the magmatic collapse, and so rifting here was magma poor. Whereas here, the first phase of rifting was magma poor. When you formed the Rockall Basin and the North Sea, there was no magmatism. But after the polyphase rifting, you started to impregnate the mantle, and coming to an end with the magma-rich breakup here. So at the very end of the polyphase rifting. So just to sum up, the main conclusions that I want you to take home is that the only difference between narrow immature oceans and wide oceans are the nature of the mantle beneath the seafloor, I would say, because in the case of a mature ocean, you have depleted mantle, while you don't have depleted mantle in the case of an immature ocean. And this may have implication on the subsequent orogeny, with the creation of a magmatic arc and depletion of the mantle when the subduction is protracted of a mature oceanic crust. And in contrast, when the ocean is small, narrow, you don't create magmatic arc, and you preserve much more inheritance and fertile mantle beneath the orogen. And if I want to make a step further, I would propose that we cannot only have one Wilson cycle. We could illustrate the classical Wilson cycle, where the orogen follows rifting follows orogeny and is followed by rifting again. This would be the case of the Caledonides. But we could also consider a shortcut shortcut Wilson cycle, where hyperextension and continental collision is followed by magmatic orogenic collapse, which depletes the mantle and form a barrier to rifting, I would say. So here, this is the end.
Thank you very much, Pauline. We have time for a few questions. Gary, is that a question?
Okay. Hi, Pauline. How are you doing?
Hi, Gary. Thank you. I'm well.
Nice presentation. But I'm bothered by the fact that surely the arrival of the magma-rich component, surely the magma-rich margin is primarily relates to the arrival of the Icelandic plume. So if there was no Icelandic plume, the Caledonide system and the Variscan system are basically the same if there was no plume. But the plume, of course, has done huge damage and allows the development of a large outpouring, a late stage large outpouring of magma.
Well, I understand your point, but what I think is that the Iceland plume should be restricted to an area that is more or less circular around the Iceland, and yet we observe magmatism much further north and south on either side. So it's not sure that the excess magma is only related to this, but could also be related to an excessively fertile mantle. Otherwise, we would have a magmatic addition all the way around here.
But as you well know, we call this a magma-rich margin, but it was only in the Paleocene that it actually received any magma. For the entire development all the way back to the Devonian, there was really no magma. So,
yes.
So there could be something special just related to the Paleocene, which is really a 2,000 kilometer diameter plume.
Yes, the magma was contemporaneous with the final breakup, and it was not contemporaneous with the rifting. And it's what I mentioned when I say there is no magma when you form the rock hole at first, when you form the rock hole and the here, the North Sea. So this would be a phase of extension during which you fertilize the mantle, which is the processes that is represented here. And this fertile mantle would then be the source for the excess magmatic event that happened at the time of breakup.
Thank you.
Thank you.
We have way too many questions that we can go through all of them. Suzanne, I think your question is almost answered with this. Mr. Winch. Who were the next?
Second chance to ask a question. I'm wondering about the reactivation. The ductile fabrics at upper amphibolite facies had to be exhumed by 20 or more kilometers of vertical exhumation, which is then followed by the brittle deformation. And so I'm wondering if the localization of both the ductile and brittle structures are both a reflection of even deeper discontinuities in the lowest crust or in the lithospheric mantle. So they're both consequence, not the brittle is consequence of ductile.
So I think you are, tell me if I'm right, but you are talking about local structures, right?
Yes.
Okay.
Maybe it's also for the other two speakers, the question.
Yeah, it's what I was thinking. That was much more the topic of the other, because here I'm much more focused on the very large scale inheritance, and in particular the mantle composition. But now specific structure are reactivated essentially depending on their orientation with respect to the stress field. So similar weaknesses can be reactivated or not depending on the stress direction.
Okay.
I'm not sure if you are speaking about a specific feature, but I'm not sure I know it.
Yes.
Maybe we can have one last question by Drow. That's a nice one. Could you ask it yourself, and then we finish this discussion?
Hello, can you hear me?
Hello, yes.
Yes, so I'm a little bit surprised because your model seems to imply that there was almost no subduction zones in the Variscan.
So there
are
was
fully developed. And my question is, what are the evidence for that?
So there was one large subduction in the Variscan realm. It was the Reik Ocean here. But it was the only one. Then there was the Saxo-Thuringian and I don't remember the name of the other, just slipped on my mind. But there was no arc in here. So subduction may have been larger, basins may have been larger here in the Central Europe, but here in the very Western Europe, there is no evidence for arc, and the paleogeographic studies did find that there was no evidence for oceans wider than 1,000 kilometers.
But that's 1,000 kilometers, still quite big. Huh? If you close that, you'll have a true subduction zone.
Yes, if it was 1,000, but keep in mind that from the 1,000 kilometers, you have to subtract the margins on each side, which are I would say, on average, 150 kilometers wide on each side. So 1,000 minus 300, you are left with only 700 kilometers of ocean. So
which still goes down to the 660 discontinuity.
No, because you don't subduct with at right angle. In the upper mantle, the slab is dips only with an angle of 50 to 60 degrees, not more.
But okay, but still, it will be a true subduction zone.
Yeah, but we don't have evidence for magmatic arcs, so we
have in Southwest Iberia a few, but yeah.
Yeah, it's from the Rheic Ocean, I think.
Okay.
Not from the other smaller Saxo-Thuringian ocean.
And could those smaller basins be back arc basins of the main subduction zones?
Well, this is extremely disputed because even the polarity of the subduction is not clearly has not been clearly assessed. So some studies, yes, they say that some of those basins could be back arc basin, but yeah, it's disputed.
Okay, because you can look to Southwest Iberia because we have back arc volcanism in both sides. So it seems there was a flip in subduction zones.
Yeah, maybe. Yeah.
And with a lot of calco-alkaline volcanism, and so a lot of these we interpret these small basins, a lot of them as back arc basins, related with
it would be
major subduction zone.
Interesting to.
Okay, just I don't dislike your model, but I think it need to be careful in this point, saying that it's not a major ocean or that you will not have subduction zones, because I think you'll have subduction zones.
Yeah, I have subduction zones for sure, but the major one is the Rheic Ocean, and it's to my knowledge, is the only one that produces significant magmatic arc.
Okay, thank you for your talk.
Thank you.